We begin the discussion of Lab 7 by defining a few of the angular quantities. Angular velocity, omega, is the rate at which an object rotates and is given in units of radians per second. Dividing the tangential velocity by the radius to the axis of rotation gives the angular velocity. Angular acceleration, alpha, is the rate at which an object increases its rotational rate in radians per second squared. Dividing the tangential acceleration by the radius will give angular acceleration. The application of torque, tau, is what causes an object to angularly accelerate. Multiplying the tangential force by the radius at which the force is applied gives the torque. Imagine a point particle with mass m rotating about some axis at a radius r. The tangential force and acceleration are related through Newton's second law, F equals ma. Multiplying both sides by the radius r, and then multiplying the right-hand side by 1, written as r divided by r, yields F times r equals mr squared times a divided by r. This is just torque equals I alpha, where I for this single particle is mr squared. Here then is the equivalent of Newton's second law for a rotating object. Torque equals I alpha. More torque will lead to more angular acceleration. For more complicated rotating objects, the moment of inertia is found by adding the moments of inertia of all the small particles composing the object, each with its own individual mass m sub I and radius r sub I. For an individual particle, the summation formula for I still just results in mr squared, and for a thin ring of mass, capital M, all of the contributing particles are located at the same radius, capital R, from the center. Their summed moments of inertia all add up to capital M times capital R squared. A large moment of inertia is obtained when large amounts of mass are located far from the center of rotation. The large moment of inertia of this flywheel was used to keep the steam engine cycling at a steady rate. It may take a lot of torque to start this wheel turning, but it will also take a lot of torque to stop it. Since angular acceleration is proportional to the torque, a graph of torque tau versus angular acceleration alpha should be a straight line, with a slope given by the moment of inertia of the rotating object. In this lab, the rotating object is just a wheelbarrow wheel. The apparatus may be assembled as follows. A post is placed vertically in a table clamp. A smart pulley is attached near the base. A force sensor is mounted facing downward above the smart pulley. A platform of wood beneath a table stand puts the wheel at the same height as the smart pulley. A string wrapped around the wheel passes over the smart pulley and supports a movable pulley and then attaches to the force sensor. Before wrapping the string around the wheel, its end may be fixed to the edge of the wheel using tape. Adjust the positioning of the force sensor to make the string segments to the movable pulley vertical. We don't want the force sensor to be measuring only a component of the string tension. Also, the wheel should be positioned such that the smart pulley is aligned with the string, leaving the tangent of the wheel. Open Data Studio and indicate that a smart pulley is to be used. Also indicate that a force sensor will collect data at a rate of at least 100 Hz. Calibrate the force sensor by removing tension from the string, specifying 0 force, and taking a reading. Then hang 500 grams, indicate 4.9 newtons of force, and take the second reading. It's worth taking a couple of moments to hang and remove the weight to double check the calibration. Now hang a small weight from the movable pulley, click Start, and allow the torque from the string tension to angularly accelerate the wheel. The upper plot is tangential velocity versus time, as recorded by the smart pulley. The lower plot is force versus time from the force sensor. Increase the numerical accuracy of the velocity and force displays to 3 places behind the decimal. Drag over a linear section and record the slope of the velocity graph to get tangential acceleration. Also record the mean value of the force for this same region. Attach more weight to the movable pulley and repeat the measurements with more torque and more angular acceleration. Here you see that the speed increases more rapidly when more force is applied through the string at the edge of the wheel. Here the experiment is repeated with even more accelerating force. The resulting acceleration is even greater. Open graphical analysis and prepare columns for accelerations and then forces. Measure the radius of the wheel by dividing the diameter by 2. A new calculated column of angular accelerations may be defined by dividing the tangential accelerations by the radius r, whatever that number is in meters. Create a new calculated column of torque by multiplying the tangential force, string tension, by the radius of the wheel. Plot torque versus angular acceleration and perform a linear fit. The slope of the resulting straight line should be the moment of inertia of the wheel. Numerically, you should expect a fairly small number, since 1 kilogram rotating 1 meter from the axis would produce only 1 SI unit of moment of inertia. Your wheel may have a mass near a kilogram, but the typical radius from the axis of rotation is much less than a meter. In the second part of this lab, we will investigate the conservation of angular momentum. The blade on this mower has a large amount of angular momentum and is difficult to stop. As we run down the list comparing linear with angular quantities, we see that linear velocity becomes angular velocity, omega, linear acceleration becomes angular acceleration, alpha, force becomes torque, tau, and mass becomes moment of inertia, I. Since linear momentum is the product of mass times velocity, it makes sense to define angular momentum, L, as a product of moment of inertia times angular velocity. Thus, L equals I omega. Angular momentum is of interest because, in the absence of external torques, it is conserved. Imagine one wheel spinning initially with a moment of inertia I1 at an angular velocity omega 1. When a second wheel is dropped on the first and they stick together to both spin, the final moment of inertia is the sum of each moment of inertia. By conservation of angular momentum, the final angular velocity is the ratio of the initial and final moments of inertia times the initial angular velocity. If the two wheels are identical, then the final moment of inertia is twice the initial moment of inertia, and so the angular velocity after the collision is expected to be 1/2 of the original angular velocity. Here we drop a stationary wheel onto a rotating wheel. The free pulley without weight allows the smart pulley to record the velocity of the edge of the wheel before and after the collision. The initial speed is recorded from the mean of a few values just before the collision. The final speed is recorded just after the collision. Note that the final velocity is approximately 1/2 of the initial velocity. The angular velocities are obtained simply by dividing the tangential velocities by the radius of the wheel. We then drop a relatively massive ring onto a spinning wheel. By noting how much the final angular velocity is reduced relative to the initial angular velocity, we can determine the moment of inertia of the ring. This moment of inertia is to be compared with the predicted mass times radius squared.